All right, here we are going to look at the definition of impedance, a reactance of an AC circuit. So, by definition, the reactance, the symbol it says, is defined as the opposition offered to the passage of an AC current by either the inductor or capacitor or both of them. Reactance due to an inductor is called the inductive reactance, and the reactance due to the capacitor is called the capacitive what? Reactance. And now I've already explained that in my previous video. So the inductive reactance XL is giving us 2 pi FL. Remember that the symbol for an inductor is L, and the capacitive reactance XC is equal to 1 over 2 pi FC. Okay, so the impedance Z is the overall opposition offered to the passage of an AC current in a mixed circuit containing a resistor and any one or both of an inductor and a capacitor. Reactance and impedance are both measured in what? Ohms. So they are, because they are opposition, they are resistance, so they are measured in what? Ohms. So the impedance is giving us what? Z. The impedance of an inductive of a purely resistive circuit, a circuit that contains a resistor only, will be equal to R, will be equal to the resistance. So if it contains an inductor only, then the impedance will be equal to the inductive reactance. If it contains a capacitor only, then the impedance will be equal to the capacitive what? Reactance. So, but overall, the impedance is the opposition to the flow of current and AC circuit offered by the resistor, the inductor, and the capacitor. It can be either a resistor and inductor, or a resistor and a capacitor, or a resistor and both inductor and what? A capacitor. Okay. Next, we're going to look at the power in an AC circuit. So for an a resistive circuit, the power, or the average power, is given as IRMS times VRMS. So that's the power. For an inductive circuit, for inductive and capacitive circuit, the power is reactive. So the power is equal to what? 0. They are called reactive what? Power. So their power is equal to what? 0. So it therefore means that power is only dissipated in the resistor. That's what it means. So that's why we have the power in the resistor. So the power dissipated in AC circuit is the IRMS current times the VRMS what? Current. So we can just simply say that P is equals to what? IV. Okay. Okay, now we're going to take a look at RLC circuits. RLC circuit means resistor, inductor, and capacitors connected in series. So that's the meaning of RLC circuits. Okay, so I'm going to draw this. An RLC circuit will have a resistor connected in series with an inductor and a capacitor. So this is a series. This is a series. So this is the voltage VRMS and the frequency in hertz as usual. So this is the resistor, the inductor, and the capacitor. So this is a series LROC circuit. So it's a series LROC circuit. Now, since this is a series circuit, there's going to be a voltage drop across the resistor. So I'll name that VRO. The voltage drop across the inductor is VL, and the voltage drop across the capacitor, I'll call that VC. Now, for a normal DC circuit, you can just add the voltages together because they are in series. But because they have both magnitude and direction, you cannot add them together in such a way like that. It therefore means that the voltages can be expressed with this formula: V of Vrms squared. Okay, let me before I go to that, we can use a phasor diagram to represent this. So let's see. If I have this, the voltage in the inductor, remember the inductive circuit, the voltage leads the current. Okay, the voltage leads the current, so the voltage will be on this side. Then the voltage for this lacks the current for the capacitor, so this is going to be VC. Okay, then for a pure resistive circuit, remember the voltage is in phase with the current, so the voltage VRO will be on this side. Okay, what we just do is this is on a straight line. It therefore means the resultant of this is going to be VL minus VC. Okay, so since VL, we have this part is VS minus, then I can reduce this to become something like this. This circuit can simply become something like this, the diagram rather. So this becomes VL minus VC, and this is VRO. Now we can just complete this using Pythagoras theorem. Just complete this way. Okay, phasor diagram. See, they are phasors, they are vectors. Okay, this will represent V, which is the VRMS that we have here. So if you look at this side will be equal to that. So this is going to be VL minus VC. So if you see, if I applied Pythagoras theorem here, I'm going to have V squared. It's going to be equal to this, the square of this, VRO squared plus VL minus VC squared. So from here you can see that the VRMS voltage is equal to the square root of VR squared plus VL minus VC all squared. So this is the voltage, the magnitude of the voltage, in the inductive in the RLC circuit. Next, this is going to be the phase angle phi. Okay, so to get the phase angle, we can use tan theta. The phase angle is going to be equal to arctan VL minus VC divided by VR. This is just simply tan theta is equal to opposite over adjacent. When you do that, so the opposite is this and the adjacent is this. So the magnitude of the voltage is this, the RMS voltage, and the phase angle. Okay, this should not be theta, this should be phi. Okay, the phase angle is calculated using. We're going to take some examples on this. Now what I'm going to do is this. I'm going to reduce this circuit to a ROL series circuit only.